So we will cover all of these topics and more in the panel today. We have recruited really a nice array of panelists ranging from academia to industry to government projects to a genuine climate expert to work with us. I just want to make sure that that all of the panelists, I see Anne, I see Martin, Karim, and hopefully Sumit is here as well. So I think we're just about ready to start the panel. Before I go on, I also want to point out that this is being co-organized with Professor Ashik Anjum, who's the general chair of the local organizing committee, and has done I think a superb job of organizing this conference along with his partners. You can find those in the UCC-conference.org and VDCat-conference.org web pages. Really dozens of people have contributed to this excellent conference. And Professor Omer Rana of Cardiff University, who is also Dean of International at the university in the College of Engineering. Omer, are you with us? Actually see Omer on the list. I do. You're muted, Omer. Okay. Well, so we have assembled this panel, and we've developed a set of questions that we've provided to them in advance. In addition, I do want to, I see Omer responding, he's here but can't currently unmute. Let's see.
Alan, can you please make Omer co-host as well?
Yes, I will do that right now. Okay, and I do need to make sure that the rest of the panelists can speak. So I should make them co-host as well, Joseph, is that right?
Yes, everybody who is a speaker.
Okay, so I will do that. Give me just a moment to make through the list. So Martin, are you able to speak? Do not yet hear Martin.
No, he's not, Alan. I think Kareem can do it now, but not Martin.
Hello, I can speak.
Oh, excellent. All right, Anne, are you able to participate here?
I'm here. Can you hear me?
Excellent. I'm just looking for the rest. Joseph, you might have to help me with this.
Let me do it, Alan. You continue.
Yeah, great. So we'll need to get Karim, Sumit, and Andreas on.
Mm-hmm.
All right. Omer, did you have any other opening remarks you'd like to make on the panel?
No, I think that we have a bunch of questions already on the website. I think it's really interesting to given the fact that the UK just hosted the COP26 conference, and climate change in particular, the impact of computing on climate change is really significant. And for me, the key aspect to consider is also electronic waste. We have all these big data centers who have these big components that we use. And when these components come to the end of their life, they often end up in landfills. So the question is, this movement that is occurring across the world, the right to repair movement, where people should be given the option to be able to repair these components, augment them, and reuse them rather than just throw them away and then restart from scratch. So I think I'd really love to have some discussion around that as part of the panel. Thanks, Alan.
Yes, if you'll allow me just a moment of shameless advertising of our own work here at Texas Tech. I know that Omer, you're deeply involved in areas of research associated with this panel. So our own interests may creep into our questions, but I just want to point out that Texas Tech has an Industry University Cooperative Research Center funded by the National Science Foundation called the Cloud and Autonomic Computing Center that I co-direct. It's a multi-university, you see the university is on the bottom, multi-industry industry university cooperative research center. And I've learned to say that quickly over many years. One of the projects we have we focus in general on cloud and autonomic, basically highly automated, self-repairing, self-managing systems. And we're focusing a lot of our work on automating operation of remote data centers. So remote meaning you don't have to go in as often. I also direct the High Performance Computing Center here at Texas Tech, and I know how often one has to intervene with the machines in a typical academic computing facility. As we migrate to the cloud, we need to be able to operate things that are as complex as scientific workloads, which often require a great deal of intervention and quite a bit more care and feeding of the equipment than is common in industry. We also need to figure out how to run these things at the locations that are sources of renewable energy. And this will be in our question set. So we have here at Texas Tech a multimodal solar array, wind farm, generator, and something that looks like an electrical substation in a building with a very high degree of instrumentation and automation that we use to study microgrids as in the context of multiple sources of energy for data centers. And I'll stop with the shameless advertising there, and I think we should go on to the panel. So let's just get people to go through and introduce themselves. If you would, let's start with Karim.
Hello, good afternoon, everyone. My name is Karim Jim. I'm from the School of Computing, University of Leeds, and I'm a member of the Distributed Systems and Services Research Group. The group has a strong interest in energy efficiency in general, looking very much at cloud computing first, edge computing, and HPC again in general. So Alan, would like me to share some slides now or later on?
We'll come back for that, but just start with
that's me. Thank you.
Great. All right. We also have Martin Bouchard, the co-founder and president of QScale, a recent startup in Canada. Martin, would you introduce yourself?
Hello, everyone. My name is Martin Bouchard. I'm co-founder of QScale, a specialized data center for computing, HPC AI, powered by renewable energy. And on top of that, we add heat recoveries to do something with this massive amount of heat that is being generated by the computers. So I'm really looking forward to talk with you on this subject.
Great. We have Sumit Puri of Liquid, CEO and co-founder of Liquid, which is an ambitious startup in the area of composable computing from the US. Sumit, can you introduce yourself, please?
Yeah, good afternoon, everyone. Thanks for the opportunity today. My name is Sumit Puri, 25 plus years in tech. As mentioned, Liquid is focused on composable disaggregated infrastructure, moving towards what we refer to as the dynamic data center with a very simple mission. If we can increase the utilization rates of that very expensive power-hungry hardware that we are deploying inside the data center, we can have a nice impact on the overall environment. And so excited to share our thoughts with you guys today. Thank you.
Great. We have Andreas Weers, who is the managing director of Psychos and is representing the European Technology Platform for High Performance Computing, who has recently run a panel at the Supercomputing Conference with a focus on Europe. We're very excited to hear about the activities on sustainability being pursued by that project. Andreas is from Germany. Would you introduce yourself, please?
Yes, sure. Thank you. Yeah, my background is actually technology transfer. So Psychos is a company owned by Stuttgart University. Probably some of you know the HLRS, the High Performance Computing Center there, and the Karlsruhe Institute of Technology. And my task is actually to support SMEs in our home state in the uptake of data analytics, AI, and HPC. And in this context, Of course, I also came around the topic sustainability. So when now the ETP for HPC, the European Technology Platform for HPC, put that on its agenda, well, I was on board, and so I'm not technically into the topic, but I'm looking at it more from the, well, yeah, technology transfer side, and what SMEs, how industry looks at it. And I'm looking forward to be with all of you on the panel. Thank you.
Thanks so much, Andreas. The SMEs are small and medium enterprises, for those not conversant with European bureau speak, but a very big focus in the Europe, Middle East, and Africa, are called so-called EMEA area, to use another piece of jargon. And so this is a big focus and a big area that we'd like to penetrate. Finally, to me, one of the highlights for the panel, Ann Stoner, Dr. Ann Stoner, who is a research associate here at the Climate Center of Texas Tech University, working with Catherine Hayhoe, you may have heard of, and really a long-standing experienced researcher who uses HPC in her own research. Ann, could you introduce yourself, please?
Hi, my name is Ann Stoner. I'm a research professor at Texas Tech and part of the Climate Center there. So I don't know a lot of the background that goes into all the computing that you guys are experts in, but I'm a climate scientist and I use the HPC a lot because we have quite a lot of data that I'll show you a little bit of how that works later. But I really enjoy using the high performance computing center. It's a lot of fun.
Yes, so Ann, first apologies for the inadvertent demotion. I think you sent me an old bio. You are definitely a research professor here, and I apologize for that. You might want to queue up your slides, because I think we'll have you start what we asked each of the participants to prepare a set of slides. And I think it's best if we start with the climate science. If you would go ahead and share your screen.
Sure. So I misunderstood the Zoom background. I put it on the background of my slides instead.
Well, that's okay too.
Oh, and I'm not even on the first page. There we go. So I'll just discuss a little bit about, or introduce a little bit about high performance computing and climate science and why it is important. So I work with output from global climate models, and those are models that are used by climate scientists and earth scientists to simulate the Earth's climate system and in response to the choices we make as humans, so energy choices and so on. They simulate different processes and interactions, the physics and chemistry and biology that happens both in the atmosphere and in the oceans, on land. Some of those processes, they include radiative transfer functions, fluid dynamics, the hydrological cycle, land surface processes, atmospheric chemistry, and so on. There's a schematic on the left that shows some of these interactions. So there's a lot to keep track of. So the climate models work by dividing the globe into a grid, as you can see on the right, both in the horizontal direction and the vertical direction. There's ocean model, atmosphere models, there's ice models, there's land surface models, and a lot of different models that kind of come together. And each grid cell has calculations and of different variables for all these different systems. And then there's also interactions between the grid cells, both in the horizontal and the vertical direction. So a climate model is very complex. We don't run the climate models at Texas Tech or at my group, but we use the output. So because the scientific understanding of the climate, it keeps evolving, there's always more climate processes that come into the models. And so the complexity keeps increasing. So that's why we need the high performance computing resources, and that need also keeps growing. Let's see, there we go. So we can get a lot of information out of climate models, but they're still too coarse to use for local impact assessments. So if we want to look at a region or a city, so on the left is an image of what the typical resolution of a climate model looks like for the United States. They're typically on the order of 100 kilometers by 100 kilometers per grid cell. So that can cover, that's a large area where you don't really get a lot of detail if you want to look at a city, for example. For local impact assessments and research, we need much higher resolution projections that can be tailored to a specific region or a location, or sometimes even a specific asset. So we need single point climate projections, either at a weather station or on a fine grid. And that is, there's an example on the right. So this is just a map of temperature for one particular day where there's like a sharp cold front coming down through the country. So you can see there's a very big difference between the left and the right. And what we have on the right, and even finer scale than that, is what we would like to work with, but obviously that requires even more computational resources. So what we do at Texas Tech is downscaling. So that's getting it from that coarser grid to the finer grid. So we can actually use that for different research or impact assessments. There's two main techniques that can do this downscaling. One is regional climate models, which is a climate model just for a smaller region like North America instead of for the whole globe. And it runs like a climate model, but on a finer grid. And then there's statistical downscaling with bias correction, and that's what my group does at Texas Tech. And we generally also do that on a subset, on a regional subset, because we can't handle data for the whole globe at the same time. Here's another image that kind of shows how coarse global model output actually is. If you go look at a region, this is the US Northeast, and on the left is what a typical climate model output would look like, and you just get one value of temperature or precipitation or something for each grid cell. And then on the right is downscaled, where you get a lot more finer or high resolution information. So climate data is big data, and it requires petabytes of storage or more. It keeps growing as climate models becoming higher and higher resolution, and includes more processes and so on. It also requires a lot of memory. If I want to work with just, I feel like I missed a slide. Yes, oh, somehow I skipped through this one. Sorry, I'll come back to that. So one climate model is not even enough. We don't know what's going to happen in the future. We don't know how we're going to evolve and the choices we're going to make to transition to clean and renewable energy. So there's different scenarios of how the future might change. The left shows different global temperature projections out to 2100 for 5 different scenarios. So each model is run for different scenarios, but there's also different ensembles within each model, because just to capture some of the uncertainty within a model. Plus then there's at least 50 different global climate models that are developed by different modeling groups around the world. So it just keeps multiplying the amount of data that we use. We at Texas Tech, we work with at least 30 different climate models and 4 different future scenarios. And it really becomes quite a lot. Okay, back to here. So obviously we need a lot of storage. We need a lot of memory. When we look at one variable for continental US downscaled to about 5 kilometer resolution, that's just 100 gigabytes for 1950 to 2021, and that, or to 2100. And that's what I typically work with. If you want to bring in more climate models, obviously that increases. We also need, when we use the high performance computing centers, we need it to have capabilities to work with different languages where we can parallelize the code to make everything faster. And also ways to collaborate and share with colleagues, so gigabit Ethernet speeds. But the center really helps us provide faster and more accurate climate science. And then the need for the high performance computing and climate science, it seems to grow proportionally with the evolution of the HPC capabilities. So we will continue to be a big user.
Thanks, Em. That's great. I really thought it was nice to be able to start the panel with a discussion of the climate science that drives us all to look at this, and also the role of computing in helping us to address this. Yeah, the challenges certainly continue to grow, and fortunately our computing capabilities continue to grow. These days, a well-equipped academic center can easily field tens of thousands of CPUs, where just a few years ago that wasn't so possible. And the national and international scale supercomputing facilities are in the millions of cores, now approaching exascale. I'd like to turn, if I could, to Andreas next, to try to give us, fill in the picture a little bit more on sustainability beyond just energy and some of the focuses of the project that he participates in. Andreas, you're muted.
Thank you. I hate it when Zoom reorganizes the windows once you start screen sharing. So, but thanks again. As you pointed out, Ellen, when I started, my background is I'm here with ETP for HPC actually. So that's what I'm going to present. We are writing there currently a white paper. And I don't want to miss to make clear that this is not only my work, but in fact, we are a team of at least 5 who are really working on this. We started in summer, so to speak, and to be delivered, we promised before Christmas. So yeah, there's some polishing that needs to be done. And it will be published next year. And what I would like to focus here on, I of course cannot fully present what we are doing, but we developed a set of key insights, and we came up with key recommendations. And a few of those I would like just to present here as input for discussion. So what we found out is that in many cases, the emphasis when we talk about sustainability in and around HPC is kind of on performance per watt. They look at the energy efficiency of the CPU, of the system, and that's just a perception, so to speak, that we have. But we think that this is too narrow. We also notice that the CO2 footprint, and if we for now just stay with this measure, is influenced significantly beyond the operation phase. So it's not only the direct operation, the energy usage of the system, but there is, of course, in the construction, in the design of the system that has significant influence. There's the software development, which has influence, but there's also the, let's say, as we say in Germany, recycling phase, or the after use phase, where again, it could make a big difference how you handle this material. The computers built out of how the CO2 footprint actually looks like. What we also noticed, and this is probably something that will be discussed, especially with hardware vendors a little bit, they probably have a different view, but we have the feeling that the lack of growth, let's say in clock speed, and we see, of course, more cores, but we think that the useful lifetime of a given HPC system might be a little bit longer in the future, which is actually a good thing if you look at it from the sustainability perspective. So And what we also noticed is, and this is a little bit related to the useful lifetime, when we have more industrial users, and if we, well, of course, the climate guys, they are really top-notch. Actually, I think any given system can be utilized fully by climate researchers by just, well, making their mesh finer. But if we look at industrial users, they are not at this level, but they are increasingly using HPC, and they have to integrate the HPC work into their workflow. So the simulation, etc., will be closely integrated. And they will also benefit if they are longer lifetimes, because their workflows can be more stable. They don't actually like to change systems all the time. They need a more reliable. Sometimes there are even legal issues that force them to keep, for example, even with older software versions for repeatability issues. And looking quickly at the key or some of the key recommendations, of course, all of them will be presented in our white paper, but I would like to give you first hint. We think that it will be very important to develop the ecosystem around HPC, and this covers HPDA and data analytics and AI as well, that systems shall be more modular, and that the focus will be put more on the optimization of the overall solution. So not only single parts, of course, they will also be optimized, but it makes sense to really open the focus and look at systems from a higher perspective. And especially when you emphasize on solutions that are based on large-scale workflows, it's very, very important to take this into account. And what's a key element, if we want to be successful there, is that we have, well, to bring all these different stakeholders together, because if you're not looking only at performance per watt, but at the whole system and the development of software and recycling and production phase, you need to bring them together, because sometimes a little bit more effort in an early stage will have much more positive effects in a later stage. And it's very important to increase the awareness of the roles they could play in there. And this is definitely a mid to long-term issue, but we think it's really mandatory. It's very important in order to have significant progress. And well, that's for now my input. As I said in the beginning of 2022, the first quarter probably, we will be able to tell more about our white paper.
Thanks so much, Andreas. It's really interesting work, and I think we have many projects of interest in the US that parallel this, so I hope we'll stay in touch. I'd like to go next to Karim. I understand, Karim, your work is in the area of energy at the edge and the interactions related to that. Energy efficiency.
That's right. Yeah, that's right. So can you see my slides?
Yes, please go ahead.
So I thank you, everyone. I've decided to give again a short presentation on some work we've done at the University of Leeds. This work is part of a number of projects, all funded by the European Commission. So I'll start just by this one. This is to do with energy efficiency in cloud computing, and the idea that we had in this EU project titled Ascetic, Adapting Service Lifecycle Toward Efficient Clouds, was basically to look at really what is out there when it comes to supporting energy efficiency in clouds. And you will realize that there is a lot of solutions, from the actual fabric, from the compute, storage, network, I would say devices, up to the actual cloud applications, going through the virtualization layer, the middleware layer, the cloud programming, the programming model and the runtime. And then we said, okay, all this works nicely. However, can we ensure that these cloud computing architecture layers can actually talk to each other and potentially support energy efficiency together, right? And that was, again, this whole idea of bringing energy efficiency awareness in every layer in this cloud architecture and ensuring that the components within the layers actually talk to each other. Of course, we had some form of an overall software stack that would obviously need to be adaptive, because at the end of the day, the cloud by definition is a very dynamic and adaptive infrastructure. So what we actually ended up doing, again, this project was certainly supported by Atos and also by HP in Italy. So we looked again at providing specific tools for the programmers, especially what we call the co-efficiency aware software design and the programming IDE. You can actually make abstraction of the environment or the infrastructure where you deploy your future services, again in a very agnostic way. We looked potentially at service energy measurement and modeling tools, again, very much at the programming level. At the middleware, we implemented the quality of service energy aware framework. And finally, we had a service deployment tool and a service operation tool. So really what happened, what the outcomes of this project was that we were able to take a specific use case from HPC and big data and demonstrate that we could get, say, up to 20% energy efficiency gain. So that was my first slide. My second slide was very much to take the same approach and to say, well, if you really look at how the world where we live today, everything has become so heterogeneous. It's heterogeneous in terms of programming models, heterogeneous in terms of hardware, in terms of hardware architectures, parallel hardware architectures, etc. So the idea was to say, well, if we forget the cloud, can we again bring some form again of solution, bringing the modeling, the design and construction of applications, again, in ensuring that the actual middleware will be able again to support the energy and the performance requirements on these potential target heterogeneous power architectures. And finally, again, look at the heterogeneity, whether again, we're talking about CPUs and GPUs and FPGAs and ASICs, etc. And then again, this idea worked perfectly nicely with us. We had again a number of use cases, especially from HPC and certainly big data. And we have again, like Ascetic, like the previous project, we have developed a whole toolkit that is certainly available on GitHub. Finally, very quickly regarding our own interest in energy efficiency, we have just started a project, again funded by the EU, called EdgeNet, which is very much to do how you do energy aware provisioning in edge computing environments. So the basic idea is to take software-defined networks and network function virtualization technologies and start thinking about a bridge towards what we see as a very attractive technology, that's serverless computing. In this case, the application performance lies with the efficient load level execution, for example, in an IoT environment, but the energy consumption is actually key because these applications may be operating in a low energy environment. And finally, can we identify the key functions that take up the most execution time, which obviously equals a cost. So the basic idea is to say, take NBF, take SDN, think about functions, and these functions will run as actually functions in a serverless computing environment. So the function itself becomes a proxy for energy usage. So hopefully we will demonstrate by the end of the project that again, they will have some energy consumption gains. Again, we will certainly keep the community informed about our outcomes. Thank you very much.
Thanks so much, Karim. And we are seeing the emergence of toolkits now in HPC and even cloud environments where researchers or users can get reports of the carbon impact of what they just did.
Yes.
I think that's an exciting area because it's relatively easy to implement compared to other changes, and it there's the old saying, you can't optimize what you don't measure.
No,
right? So,
no. Again, at the end of the day, it all starts with software. It's software that runs on those machines. So why can't we think about making software energy efficient?
Yes, software, of course, that uses hardware. So I'd like to turn to a couple of topics on a forefront hardware and software environments. So first, I'd like to ask Martin to tell us what's going on based in Quebec and what you're working on at QScale.
Thank you. I'll share my screen. Here we go. All set. Okay, great. So basically, QScale is another portion of the equation, basically meaning the infrastructure. We talk about a lot of computers or everything, but all these computers, they need a lot of power, they need a lot of space and security and cooling. So this is where QScale comes to place. So I don't need to tell you about computing that is growing at an exponential pace. It's doubling every 2.5 months. We've seen things like climate science. They need more and more and more. So this is a very great opportunity, but at the same time, for the planet, it's an issue. This energy consumption is basically, if it continues that way, and then we have this quote from this gentleman here that is basically saying that if we continue that way, the data center industry will become the largest energy consuming industry on the planet. Even if we move everybody to electric cars, we have an issue with computing. So how do we try to solve that challenge? There's no easy answer, but there's some answers. And basically, this is the mission that QScale has been working on. We've been funded like 3 years ago. And basically, we come from the traditional data center industry, but we've decided to focus on the HPC industry, the high computing opportunity. As we know, it's way different to run a traditional cloud rack or a storage or a web server versus a high HPC design. And our approach is to try to make it better for the planet by using renewable energy, which is something we're trying and starting to see in the marketplace, but also how do we recapture that heat? Because basically a computer is just generating heat from the processing. So we've been working on a design to really recapture that heat and do something good with it. And we've been working hard on leveraging that heat for agriculture at scale. So this is basically the intersection. QScale is the intersection of computing at scale, but also agriculture, or green agriculture at scale. So we believe that we need to rethink the way we do compute, and it has to start with where do we do compute. So we're lucky computing is basically not time sensitive. You can send your data somewhere and then the computers are working, for a week or a month or on something. So it's not as important to be very close to your data. There's some issues with transporting the data and things like that. But we believe that we need to start thinking about moving the processing to the best place in the world where it makes sense. And where it makes sense, we've seen a trend. It's north, where it's cold, where we have clean power, where we have space, where we have no needs for using dirty energies. So we believe that Quebec, for example, in Canada, Iceland, Nordic countries in Europe are very interesting places to run computing workloads. It comes with some challenges, of course, and we'll talk about that later on. But I think it's a mindset that we need to work on, and the good news is that it started in the last few years. So as you know, most of the computing is being done sometimes on the cloud, on premise. Unfortunately, it's mostly powered by non-renewable energy. So coal, for example. So if you run a EC2 machine on Amazon in Virginia, that's not very good for the planet. We're seeing a move to current grain standards, so renewable energy, which is a very, very interesting thing and good trend. But I think we can bring it to another level, basically meaning that we can do that, the current green standard, but also move it forward with energy recovery, which is what we're working on at QScale. And just to give you an example, if we move a 100 megawatt facility, or let's say big workloads, exascale computers, to a place like QScale, where we reuse the energy in greenhouses. As you can see on the picture, there's some greenhouses just behind the data center. It's the equivalent of remove 200,000 cars, gas car from the road. And with that heat, we can generate 83,000 tons of tomatoes, for example. So this is huge. And of course, on top of that, there's some carbon credits that we can generate through that usage of the heat to grow the food, for example. So at QScale, we've been working really, really hard on making sure that the energy is being, we're able to reuse the energy. It's a challenge because it's not as easy as just plugging a cable or a pipe. There's a mix of different types of computers or systems, and we've seen some data RAID arrays or storage servers that are more traditional, air cooled, up to a future-proof 200 kilowatt, like the Tesla or NVIDIA new computers, GPUs that are liquid cooled. So we basically work on a design that is able to accommodate at the same time traditional or current technologies, but also being able to, in the same space, work, make a supercomputer work close by a storage area server. So very efficient in terms of energy. We try to make it at scale so the costs are very low. And the good news is that we do all of that at the cheapest cost in the industry, because the clean power we have in Quebec is the lowest in the world, with some other places, but it's really abundant. So there's a lot. So we believe that it makes sense to move computing to places such as QScale. So the good news is that it's all started. It's just not just a project. We raised the money. We started constructing the whole thing. We closed a 140 megawatt of renewable power purchase agreement with Hydro-Québec, which is huge. And the funny thing is, it's just for the first campus. We believe that eventually we'll be able to fill this very quickly. And we have other sites already planned. And just to give you an idea of scale, of course, it's a picture, it's a representation, but in terms of just the greenhouses, it's the equivalent of 100 American football fields. So that's a lot of greenhouses that we can heat from that energy that is normally just going into the air. And the good news also is that we have an experienced team. This is not our first data center and the first operation. We've been working with big cloud providers in the past, but this is a very unique approach because we're really targeting the HPC supercomputer market. And we believe that this is even more impactful to work on these big projects, because cloud is one thing, it's consuming a lot, but HPC is just doubling every 3 months. It's exponential. We need to address that. And just a quick picture of the construction site. I think it's about 2 months ago, and it's quite huge. As you can see on the back, there's some foundation for the electricity, the grid. And eventually this is just, there's the first phase of the building. So it's just a quarter of the whole project. And just behind, you'll see where we can put the greenhouses. So we're really proud, we're really happy, and we're already in discussion with some very interesting clients. And we believe that there's a way to make HPC or computing good for the planet, and even at the same time help for climate science at this space. So that's it.
Thanks so much. So we've gone from the general topics related to climate science to some considerations of edge and energy efficiency, to also including some sustainability topics, to general data center optimization with respect to energy capture. Now I'd like to turn to Sumit Puri to tell us about some of the components you can put into a data center and how to optimize those through composable computing.
Thank you, Alan. Appreciate the opportunity to share with you guys. What we'll do here is we'll cover a little bit on what we see as the market dynamics, explain a little bit on what we mean by composable infrastructure, and then we'll talk about how we think it impacts the environment and how we think we can do better. So from a high level, this is the one and only market slide we'll share here. This one's from Gartner. This is the data center roadmap, kind of where we were, where we are, where we are headed. For the sake of time, I'll just kind of point out two key things here. Number one, in our belief, we think statically configured infrastructure is the old way of doing stuff. We think the future is all about dynamically reconfiguring the infrastructure based upon the workloads that we are looking to deploy. The endpoint, we believe, is the lights out autonomous data center where there's very few humans running around to move around hardware, and it's primarily done through software-defined methods. In order to get to this endpoint of the software-defined data center, we think two fundamental technologies are required. One of them is the disaggregation of the very power-hungry, expensive hardware that we're deploying inside the data center. And then number two is some very intelligent software that can take all of these disaggregated hardware pools and reconfigure or compose them into server infrastructure that we can use for our application. So let me start by explaining what we mean by composable infrastructure. Legacy servers are relatively easy to understand. We take devices, we plug them into the motherboard of the server, and that's how we define what our machine looks like. And if we want to change the configuration of that machine, we send a human to the data center with a screwdriver and we power off the infrastructure and we change the configuration. The modern approach around disaggregation, what we do is we take trays of resources, trays of just compute, trays of just storage, trays these days of GPUs, accelerators, networking cards. We're device agnostic, but instead of taking those devices and plugging them into a motherboard, we take those devices, we plug them into a switch, and we come in with software and we dynamically configure our server to whatever best match the workload that we're looking to deploy. Take this 1U pizza box, take 6 of those storage widgets, take 10 of those GPU widgets, interconnect them all together at the bare metal as if we were building a server by plugging devices in, except we define it in software. And on the other side, we get a machine, however big or small we want that machine to be. And more importantly, that machine is dynamic. So when my workload needs another NVIDIA GPU, we don't send a human down to the data center and see if there's an empty place to plug in a device. We reprogram that switch and we add or remove devices from the server depending on what the user or the application layer is looking to get done. And so what Liquid builds here is a little bit of that interconnect technology and that software, so we can take all of the hardware that our customers are buying today and turn it from statically configured to dynamic configurable infrastructure. And so when we take this approach of disaggregation and then dynamically reconfiguring the hardware, there's a tremendous amount of benefit that we see around data center architecture. I think it's easy to understand how dynamically moving a 500-watt GPU around to whatever server needs it the most has a tremendous amount of benefit, but there's a lot of other reasons why disaggregating the data center makes a lot of sense. Think about scale out, right? As we scale out our HPC environment, you can add trays of just storage, add trays of just compute, add trays of whatever resource you want without paying for all of the other items, right? We can decouple our purchasing decisions. Add more compute without paying for more GPU, add more storage without paying for more networking. Let's deploy the power hungry resources as we need them. Let's not go burn a bunch of compute just to go get some additional GPUs. This was mentioned earlier around brownfield, right? We think there's a tremendous opportunity to give new life to the infrastructure that we've already invested in. Let us come in with trays of storage, trays of GPUs, trays of networking, and add them to the existing infrastructure that we've already deployed. Let's not do the rip and replace and waste all of it, right? We can build new configurations that are not currently possible today because today we're confined by a piece of sheet metal. There's benefits around software efficiency, right? Today, most software is charged by x86 processor. If we can decouple the x86 from the device, many times we can actually save on software licensing also. And at the end of the day, where this really matters is really around resource utilization and efficiency. There is no bigger knob that we can turn inside the data center around the environmental impact than utilization rate. If we can take a rack of power hungry infrastructure that's sitting 20% utilized because it's statically configured, dynamically reconfigure it to wherever those resources are best utilized and squeeze 40, 50, 60% utilization out of that same hardware, that is the best impact that we can have on power, cooling, water consumption, floor space inside the data center. And so, a lot of different benefits to taking a disaggregated approach, but at the end of the day, the thing that we are looking to address is the tremendous amount of waste that happens inside the data center. Underutilization, oversized infrastructure, infrastructure sitting idle, burning power and not providing any benefit. And so we think a lot of that is driven by the fact that things are statically configured. And if we can disaggregate, rearrange things on the fly, literally in seconds, we think we can squeeze much higher utilization rates, do more with less, and we think that impacts the environment more than anything else. And so we just also raised a nice round of funding. And one of the theses that we really leaned on was the ability for dynamic architectures to have a dramatic impact on the environment. And these are some statistics that maybe most people don't know, but data center growth is huge. 500,000 data centers grows to 8 million. 20% of the world's power by 2025 will be consumed by the data center. Where do we end up at 2050? Half the world's power is going to data centers. That's non-sustainable. The amount of carbon emissions is non-sustainable. So we as an industry must find a way to change, right? We have to get away from the old way and do more with less. And we think dynamic infrastructure that can raise utilization rates has a big opportunity to impact here. And I live in the West, and this was an eye-opener for me. The average data center consumes 3 to 5 million gallons of water per day, primarily for evaporative cooling. This is as much as a city of 30 to 50,000 people. How long before the government starts intervening here and saying, you know what, this is unsustainable. All of our water can't go to the data center. We got to take care of our people and our agriculture also, right? And so these are big problems that we're dealing with inside the industry. And we think architectures like composable really have an important, part to play here. And to that, this is what I'll close with: is we went off and we wrote a white paper specifically to talk about why the IT industry must prioritize sustainability, talk about some of the problems that we're experiencing today, and talk about how technologies like dynamic infrastructure can raise utilization rates and have a direct impact on the environment. So that's what we wanted to share today. And I'll just kind of close with lots of different areas for us to impact, everything from machine learning, deep learning, artificial intelligence centric workloads, to HPC, to traditional enterprises who want to own cloud. And we think edge is a massively important area that is going to consume a large amount of compute power. And those guys are extremely sensitive to power, cooling, and serviceability requirements. So
thanks, Sumit. And for those who think that we already are doing these things, I want to point out that the amount of time didn't really allow Sumit to get into the technical details, but there are technical differences in how clusters are composed with these composable architecture tools. If you are curious, just a quick Google search would probably find you that. The initial steps being taken with respect to PCI bus architecture extensions beyond single nodes, and in the near future, CXL and CXL2 infrastructures. So I'd like to turn to the question period and ask Professor Rana to please take the lead.
Thank you, Alan. So that was a fantastic statements from everybody. And I'd like to start with the last two speakers. And I think my first question relates very much to some of the presentations from Sumit, Martin, and Kareem. So edge computing, as you said, Sumit, and your last statement was that edge is a massively strong area and a strong growth area, which also is likely to consume a lot of power. And also, I really loved the idea that, Martin, you presented, this idea that you have a potato field behind a data center, so you could basically recoup the energy. And also, so my question was, right, that in cloud computing, as we move towards the integration of edge and data center integration, do we also consider edge energy as a common approach that we can use, more widely? So very much like the pizza boxes that Sumit mentioned, could another rack be a collection of energy sources or energy capability, which is a multi-vector energy? So you could have, wind turbines, you could have solar panels, you could have other, but they're all provided in proximity to the data center. And not just consider the data center in its own right, but the vicinity of the data center, because often we try to optimize workloads within the data center, but the data center could also influence the nearby area, very much like the example that Martin showed. So my question really is, what do you think of edge energy alongside the use of power generating stations and the use of grid resources that provide power to the data center, how could we make this more generalizable to very much like the component model that Sumit presented? So starting with maybe in reverse order, starting with Sumit.
Yeah, no, listen, I'm happy to give my opinions here. I think it's a brilliant thought. We at the end of the day, what we're focused on is raising the power efficiency of the individual rack. I guess I hadn't thought about how we actually feed the power to the rack, and at the edge, that makes tremendous sense, right? And so I can totally envision an area where solar, wind, other green renewable resources are the things that are feeding those banks of compute. So the idea makes perfectly good sense. And what I'll say is distributed computing is going to be the next big trend. The speed of light is real, and us sending that data packet back to the core is not the way that we are going to do it. So inevitably, compute must find its way out to the edge, and edge is fundamentally limited by power, floor space, cooling, human access. Those are the things that we're trying to solve. But I guess it's a really good question, and rarely am I stumped, but I love the idea of finding new ways to feed that edge infrastructure rather than burning coal and doing it the old way. So great question. I can envision it. I can see it. What I'll tell you is there's no doubt in our mind that AI-driven applications at the edge are going to be real. And I believe that things like autonomous vehicles, things like autonomous checkout at retail, all of those are going to be the next killer apps that push these power-hungry devices out to the edge. And we as an industry must come together and find a better way to solve the power problem. It's a great question. Thank you.
Thank you so much. So back to Martin. Martin, I really loved your slides, by the way. I thought they were absolutely brilliant. I think it's exactly along the lines of what I was thinking when I framed this question. So just some thoughts from you, please, and then we'll pass to Kareem.
Yes. Again, I definitely support this idea. As Sumit said, it's actually a very interesting one. I would probably add one thing is that although there is a lot of hype regarding this carbon neutrality, we also tend to think about the data center and the cloud data center in particular, because there are all sorts of subsidized renewable energy projects out there. There is always this claim that there is a 100% carbon neutrality. However, when it comes to, say, the big players like Google, they tend, of course, to have what they call their small edge points of presence, and these are not really covered by the carbon neutrality claim itself. So my message here, this is fantastic. However, we do not want, of course, to add yet more new devices on the edge of the network, consuming resources, increasing the need for the bandwidth, increasing power consumption. So this has to be done certainly in a very, I would say, clever way. That's how I would put it.
Okay, thank you, Kareem. Martin?
Yeah, I think it's really interesting, and of course at QScale we work more on the mega scale part of it, not necessarily the edge portion of it, but at the same time it's a system. And I think autonomous cars are a great example. There's some stuff you can do, I would say offline, or let's say training a model for the self-driving cars with all the data from the cars, but the car driving itself is an edge computer in a way. So how do we make this? And I think it's a brilliant idea. I think it's more distributed computing is probably the trick. So how do we push the things at the right places? So some stuff has to be done at the edge. Definitely, it has to be fast, quick, efficient, local. For example, a factory where you control the machine or something like that. But at the same time, training massive amounts of data models for climate change or trying to find a new drug. So how do we make all these things work together? And I think having a hybrid or liquid or whatever the name is the goal. It's like almost like biology, where you can reprogram things, move things. I think we need to change our mind in terms of, no, it's not just a rack. It's processing, it's data, it's moving. It could go to the right place right now because it's the electricity cost is low, or it's sunny, it's windy, and then whoop, you move your data somewhere else or something like that. I think we need to evolve in that direction. But I like that approach.
Great, thank you. Andreas, what do you think about edge energy? And then I'll come to Anne.
Well, I think it's. I agree with what's been said so far. I think I would like to open the perspective a little bit. We have we are not looking at HPC only, but we have also data sources, and they will be more and more distributed. So if we are thinking of IoT, for example, data will be probably spread all over the world, and the cost of moving data is definitely, well, it's not getting that much cheaper like computing is. So the share of moving data, also in the energy bill, so to speak, will be bigger and bigger, and this makes automatically, this focuses us, forces us to look at edge computing, to work on the data wherever possible, where it is, not move it around. And if I go beyond HPC and look at AI and words like federated learning will appear. So we will not only, this is actually distributed computing transformed on AI data analytics, and those are things that we will definitely have to look closer into. And I think the basic idea is really to add a price tag to this energy usage in whatever way, a metric actually. That's what we need, and then well, we'll at least better understand what factors are all involved there.
Fantastic. Yeah, that's very interesting. And Anne, I would love to get your thoughts, because I think the models you presented, and I'm just the scale that you presented in terms of how things have changed. I would love to see what your thoughts are.
Yeah, I think this has been, my talk didn't really fit in that you guys are trying to solve the problem with how energy is being produced by all these computing centers. And I'm talking more about climate data, but as a user of the computing centers. But I think it was really fascinating, especially to hear how the energy that's produced, like the heat energies, can be used for greenhouses. That's amazing. But also, I'm really interested in the cloud computing. I'm a consultant at a different company where we use cloud computing, and especially now during COVID, everybody's scattered around the world, and companies have figured out that you don't all have to be in one place. To have everything in the cloud and be able to all access the same data and work on it together is a huge plus for not just climate science, but anybody working on a lot of data. So it's really fascinating.
Great. Well, I can't resist the editorial urge to point out that a lot of our work here at Texas Tech, as I said at the beginning, is focused specifically on this topic of how to operate data centers that are remote, like really remote. Yes, the big cloud computing companies will advertise that they use a large amount of renewable energy, but that's just a matter of contracts. We're talking about different approaches that can actually reduce or optimize the energy use at the point of location of the data center. And that carries with it at least three implications. One is you can be more efficient about using it. The second is you have to be good at remote operation. We're talking about putting these things in cotton fields and the windswept Canadian North and so forth, where we can't expect to have full-time staff there very regularly. So that leads us to contemplate reliability at the level of the change that happened when auto manufacturers started putting computers into cars. At the time, now over 20 years ago, computers were not very reliable, and the auto manufacturing industry said, no, they have to work over 200-degree temperature range and have absolutely no failure modes. I mean, the blue screen of death takes on a whole new meaning when it occurs in your car, right? And then there will be dozens of them in the cars, and so I keep pointing out to people that the way to use computing more efficiently at the sources of renewable energy or cheap energy in general is not to focus on the energy cost savings, but to make the computers cheaper. So these trends of composable computing, simpler computing, more robust computing that can be run remotely. And then the third implication is one that takes a while to dawn on you, but when you realize that Microsoft is already building 50 to 100 data centers per year, that in Maryland, they're planning a 2,500 acre data center city, just 2 hours north of me, Facebook is building a 2 gigawatt solar array specifically for its use. You finally realize that the scale of computing you can access, if you actually solve these problems of distributing them, imagine every wind farm, or in some cases, every wind turbine as a source of energy. You can actually access scales of computing that are vastly beyond what we are able to field economically ourselves. So there are other implications, but I want to take that point and turn back to you, Anne, and say, if we could make a scale of computing, say 2 or 3 orders of magnitude larger, available to you in ways that are actually carbon friendly, but require a little more flexibility in planning your job executions and use, what would you do with that? What kind of scientific problems would you solve?
Well, the users of our data are always interested in higher resolution, not just 5 kilometers, but even 100 meters or hourly information that just takes so long to run. And for us, it's not been possible. Something like that, I think would be amazing. And even if we have to be flexible, usually we can set up jobs and submit them when we can. I think that would be amazing.
Martin, what about you? I've held out the prospect that the sort of thing you're trying to do could be scaled remarkably, and in fact, some ways could be used even to regulate the electrical grid itself. Are you prepared to scale your technologies to a much higher level and try to combine economy with carbon savings?
Definitely, and it's part of our name. So scale is for definitely scaling. I think most people don't even realize the needs for computing. Even today, even if it looks big, it's just starting. Actually, most data scientists I'm speaking to, they're always telling me the same thing. I need more computing. I need more. If you give me 10 times more computing, I will take it. But so how do we leverage this and at the same time, be kind for our planet? I think it's a human thing also, not just a technological thing. Most people, they're used to having their own servers, they have their team, but I think we need to realize the impact. So there's the cost, of course, but also if you're powered by coal, maybe, okay, you have to move some of your people to Canada for a while or something, or set up something intelligent using robotics or something. But we need to really understand the cost for the planet of running, for example, a massive computing exascale computer powered by coal. So what do we do? And what do we regulate? So do we accept that people are running massive or just buying carbon credits so there's a lot of things, and again, it's a world thing. I think it's not just a country. I think, and also the community has to take position on this, and we have to give the example and say no, it's not good. Some users we need to be close to the clients, and sometimes we don't have any other choice. But when we have the choice, we need to take it, and it starts from us, the humans, and it's a choice for our planet.
Okay, so a variation on this question, I'll throw to Karim. If we do what we're talking about here and make data centers more co-located with energy generation, then the core becomes the edge, right? Because you have an edge management problem to manage the computing itself. How do you see this playing out in light of the technologies you've discussed?
Well, it's certainly an interesting question. I mean, from the academic perspective, I will certainly think about designing some form of efficient mechanism to dynamically dispatch the request among the computing nodes, and certainly based on the current workload and the availability of the renewable energy sources themselves, because that's, again, that's to me is key. And if I'm able to tackle that problem, I will think about minimizing the service time, for example, while keeping the renewable energy utilization and the stability at a satisfactory level. Again, I think there will certainly, I will certainly see it as an optimization problem out there.
Right, and as Sumit has put into our chat, you know, doing more with less to increase the utilization rates. I think this actually is relevant as well. If you imagine a distributed set of generalized data centers, then each one of them has got to be somewhat flexible in the workloads it can take on. And so perhaps there's some tie in there. I guess I'll throw it back to Omer. Do you want to ask more questions or throw it to the audience?
No, I think we can go to the audience. I just wanted to just mention, I think maybe just give Sumit and Reyes also a chance to maybe comment on that last question. I guess one thing maybe people haven't commented on is renewable energy is very dynamic and variable. You know, the frequency at which you have the generation, especially with wind turbines. So the use of, you know, battery sources and storage sources on site can also play a very important role. So it's not just about renewable energy and data center, but other components in the ecosystem that may also need to be produced as a way to balance, you know, renewable generation with demand. I just wanted to come back on your last question, Alan, to Sumit and Andreas, and then we can open it for question. What do you think?
Yeah, I'll just add one quick comment here. Sorry, I was responding in the chat window to a previous question that somebody was asking around, you know, how do we actually go off and solve this problem related to water consumption? And, you know, my fundamental answer for most of these things is the same. Yes, we must move to better sources of energy. We must move to renewable sources of energy. At the same time, we must get more efficient at the rack itself, right? And so I always go back to, you know, if we're able to take that 400-watt GPU and do twice as much work out of that single device, that's a much better answer than deploying two of them, right? And that's just the direction that we need to head.
Yeah, and well, if I may follow up on this, I think we heard almost all the ideas and the components that would help there. And if I look at it from the industry perspective, at first they are usually they are very cost driven, and most of the measures we discussed, they also influence cost in a positive way. So if I have a better utilization, I will use less energy, the investment will be used better. And I think if we can develop a kind of metric that puts this together, I think the parts fall into place, and they will perfectly make sense from the modular approach to the decentralized energy. We actually, the end users don't care where their computation happens, at least usually they don't do. If latency is not an issue, and which in many cases it isn't, this really can be distributed. And I think the most critical part is really to have an efficient management of all these different parts and make them run in a very, let's say, stable and productive way. And I actually don't see any contradiction here. It needs to be done. It's not simple, but I think if companies like Liquid or also Square, you're working in that direction already, and I think that's the right way.
Yeah, so I'd just like to pick up on that and reemphasize that if we do this at sufficient scales, you can actually help regulate the electrical grid itself through adjusting computing to meet demand, and to, in fact, as is well known, many sources of renewable energy overproduce at some times the cycle and are unavailable at others, as Omer has pointed out. So during times like in the middle of the winter and the wind's still blowing, wind power is essentially free, or you can even be paid to use it. And use of computing at scale can help actually regulate the frequency of the electrical grid, which is even more valuable to energy producers than regulating the load, because if you get the frequency wrong, you burn out equipment. So I think maybe it's time to turn to questions from the audience. So Omer, how would you like to organize this? We can pick them out of the chat, or we can just invite
Yeah, we can
questions.
pick them out of the chat. Maybe, Alan, do you want to pick one? Oh, there's one from Chen from Loughborough also.
Yes,
I don't know if
sure.
people can unmute.
So Azam Khan from University of Leicester asks about the use of standardization and policy. And of course, I can tell that even though the UK is not officially part of Europe anymore, the mindset of Europe is still there. Azam, you want to unmute and ask your question? Or can we?
Yeah, I don't think they can
I don't
unmute.
think you can. All right, so his question is, how effective can standardization and policy be in achieving sustainability, particularly considering the adoption of decentralization? He points out Bitcoin's annual electricity consumption is in the many, even probably above 100 terawatts, more than Finland. Is it possible to standardize or regulate trends in computing? So I guess, Andreas, you're the first one I think of when this question comes up.
Well, regulation here is already very complicated, even if you don't have computing on your plate. Well, it's a huge challenge, I would say. I wouldn't bet on it that this will happen on short notice. But what we probably can do is try to work on providing a good database basis on which then regulation can be developed. So I think we need to do it in the right order, because regulation doesn't really help if it's not based on reality. And I think we still don't know enough to go right through to regulation.
Anyone else want to comment on the role of standards? I will point out, yeah, go ahead.
Sorry, Alan, I was going to make one comment. This is actually really brilliant. I think the industry could massively benefit from coming up with some kind of standardization to measure beyond just PUE, right? Like that's like the old way of looking at the world, right? We need to take everything into account. Carbon impact, sources of energy, the amount of water consumption, overall efficiency beyond just PUE. So I think if we can do something as an industry to get this message out, including waste, right? Including infrastructure waste, right? And so to me, I think we could significantly benefit as an industry if we were to come up with some standardized method of measuring green, right? I think it would be big.
So I'd also like to point out that standards, as in the standardization process that we depend on deeply in computing in general, from software to hardware, plays a role here. The development of the CXL and CXL2 standards that I mentioned earlier are enable the kinds of technologies that Liquid and others are pursuing.
It's just that the standardization process itself may take very long.
It's true, but I've worked for more than 30 years in the area of standards, and I know all the standards jokes, so you don't have to repeat them. But I will say that it's actually how you do things. The whole web itself is nothing but a set of standards, and that new Wi-Fi system you buy wouldn't work if it weren't for the new standards, and all the improvements come through that vehicle. So I'm actually quite friendly to the idea of standard as part of the process. And I think having green standards makes sense. In computing, we always sacrifice efficiency for ease of use, always. From the beginning, we no longer code in assembly language. We given that up in favor of abstraction. And at some point, you have to draw back to efficiency. So, for example, when cell phones became, much more powerful, programmers had to go back and learn how to control the energy impact of their code in a way that they hadn't before, and that led to new chips and standards. Omer, do you want to pick it? Oh, go ahead.
Yeah, just to not be misunderstood. So I was not arguing against standardization. I was just pointing out that, as Karim also said, this is a very long process, and we got to do it right, and we cannot start with that tomorrow. But of course, I'm backing this.
So I just wanted to pick up on this idea that many in Europe generally, and we're in many ways, we're still part of Europe, guys, whether you like it or not. So I think the question here is that, you know, many organizations in Europe have declared a climate emergency, and that has a direct impact on their policies, for example, the way they operate, the way they use energy, the amount of energy they use. I think that an indirect kind of consequence would be that, you know, these standards might actually emerge bottom up because of the way that people are required to respond to the climate emergency as a consequence. So I just wanted to pick up on one question in the chat, which is the increasing kind of, I guess, growth in quantum computing. And we've seen in recent years, you know, that there's been a significant interest, especially in the national labs, on building quantum computers, and particularly in the HPC domain. So how do you see the growth of quantum? Is it more energy? Does it actually require more energy? Or how do you see the kind of trade-off between energy efficiency and quantum computing?
Maybe I can go on that topic. Actually, we had some discussions with some quantum providers, I would say, big companies with 3 letters. The funny thing, and I'm not an expert in quantum computing, but what I realize is that the main challenge with quantum computing is massive cooling. So it has to be very, very cooled down. So it's, again, an energy problem. So you need a lot of energy to cool down that system. So again, we're at the same place, and eventually, so I think that it could be, you know, deep learning, AI, HPC, quantum computing. It's always the same issue, or even transportation. It's always about energy, how you produce it, how you consume it, what's your efficiency, like you said before. So it's a complete system, and we need to rethink. And I think we've been used to be very high level. And I like this analogy of the phone, where we had to rethink. When was a teenager, I started programming, and I had to think about the memory issues, the RAMs, the GPU, the CPUs. And I think we need to go back a little bit to first principles and really think the whole thing and think about the impact for our planet. But I think quantum computing will basically have the same issues that we're seeing with AI and machine learning or HPC.
Okay, should we turn to a topic of data? Mohammed Zakaria points out that the amount of data is growing hugely. He claims computational performance improvement seems slow. It's certainly true on a per core basis. And he raises again this question of machine learning and AI to help solve the issue. I'd like to broaden it a bit and say that I'd like to ask Anne, for example, to weigh in on the degree to which sharing of data is important, and our need to develop not only smarter ways to analyze it, but better ways to distribute it is important. And you indicated that the cloud had advantages for sharing of data for your field.
Yes. So I'm new to working in the cloud, but at Texas Tech, we've generated so much data, and it's always a challenge how we're going to transfer this to people who are not part of the Texas Tech computing system. So we've used with Globus, or we've used different Dropbox, but obviously you can't use that for very large amounts of data. We tried to make links, so that's always a challenge that we have. With the cloud, I think it becomes a little easier because there's different. Now I work with the Microsoft Azure cloud computing, and there's ways of making different apps that can access the data. I haven't worked with that yet because I'm new to this, but that sharing is definitely always a challenge when we're working with so much data.
Great. I actually think one of the unanswered questions here, we've talked about distribution of computation, about energy efficiency, both within data centers and of the equipment themselves and of the data center. But you know, the idea of variable computation sort of implies that you've solved the data problem. At some point, you know, data storage systems draw power too, and making them as distributed as the computation may be a challenge. I want to point out that this panel is just the tip of the iceberg, if you will forgive the mixed metaphor. of this topic, and we do intend to come back to it to propose workshops and even conferences on this topic, because I think there's a rich set of topics to explore. Ashik Anjum from University of Leicester and co-chair of the local organizing committee for the conference. I think you have a question.
Yeah, so thanks, Alan. This is a very interesting discussion. So I was thinking that, I mean, we may probably have a little trade-off. Instead of just increasing the performance, for example, in HPC centers, to keep on moving to teraflops and petaflops and exaflops at the cost of energy. So can we tolerate a little kind of performance, a kind of sacrifice or trade-off? And if it could save energy, probably we would be better off. For example, if we have seen in the industry, for example, cars and other things, or even in aerospace, where they think that by the way, speeding up beyond a certain limit would consume basically double or triple energy. So can we do the same thing within data centers or HPC center as well? We will say that this is the maximum speed we could have, and it means that 2 to 3 days additional of the processing kind of time is tolerable. So that would have saved 50% or 30% energy. I guess that could be a way forward. I don't know, is it feasible or not? It's up to the panelists for what they suggest.
Yeah, that's a good question. So essentially, so if I were to plot performance versus energy, where are the sweet spots that we can live with, rather than always have increase in performance? So if it's a multi-criteria problem, what are the livable, if I call this concept of the Pareto front, in terms of optimization, where would be the sweet spots that Ashik mentioned? And how do you, especially, Anne, in terms of your community, what do you see? Do we really need to continue increasing the speed at which you do computation? And also Sumit, I'd love to hear your thoughts on that.
We may run out of time before we get everyone able to answer the questions, but I think it's a very interesting topic. If you've worked at all with GPUs, you're familiar with the idea of not ever being able to use the maximum capacity of every component of the card at once. And I mentioned the problem of cell phones, that certainly there's a lot more computation capability than your battery can drive, at least for very long. So there's an optimization along the lines of what Ashik mentioned. Does anyone want to pick up on this topic?
Maybe very briefly. Yeah, go ahead, Sumit.
I was just going to add one comment. Listen, I think it's a function of workload, right? This is a function of workload. There's going to be some workloads where performance is everything. I don't care. The more performance you give me, the better off I am going to be. Those tend to be like HPC centric, AI centric kind of environments a lot of times. The other side of it is there's probably a lot of edge environments, as Alan mentioned, where we have way too much processing power. And in those scenarios, running things slower because we are not latency or performance sensitive may make a tremendous amount of sense. I'll just give it to this panel here. Lots of good questions that I've never been asked before. I've been asked a lot of questions, but that was another really intelligent question. Thank you.
Yeah. I can just add very quickly that I can easily see classes of services that actually map to the application requirements, as Sumit actually put it. It's about functional, what you want to provide, again, as a service, and the quality of the service. Again, looking at the performance versus energy consumption trade-off. Again, this kind of solutions can be implemented. You could have business models around them. That's certainly, and certainly economic models behind them. One other thing that again comes to my mind is again the role of edge computing in all this. In the era of exascale computing, right? If you imagine, and in again next year, in 5 years' time, you will have all the supercomputers or exascale supercomputers all around. The aspect of data and data analysis becomes very crucial, and you will expect to see the edge computing as the extra layer where you filter the data before you send it to the actual exascale supercomputer. And that in itself brings very interesting questions about workload, energy consumption, and the rest. So we need workshops on this.
Yes, well, good point to end. I just want to thank everyone who has participated and stayed through the entire thing. We had a really good participation. We will definitely be coming back to you with requests to participate in organizing larger scale efforts. I think there is a lot of work to be done, and we do want to you know, have a planet that's livable. Dr. Heyo points out that the planet will be fine. It's our survival that we're talking about, right? So you know, the planet will outlive us if we're not careful. I wish I could think of a more positive note to end on, but Omer, maybe you have one.
No, I just want to thank everybody. Fantastic discussion. Thank you.
Okay, thanks so much, and we'll look forward to participation at future events.
Thank you, everyone.
Thank you, everybody.
Thank you.
Very
for
interesting.
organizing this.
Thank you, everyone.